For decades, a baseline working hypothesis in cognitive psychology has dictated that human conceptual organization is built on two completely distinguishable components. The first is semantic relatedness. Historically, this has been narrowed down to superordinate category coordinates, or items with high featural overlap. A horse and a dog, for example, share enough structural and categorical features to be heavily linked on a semantic axis. The second component is associative relatedness. This is defined not by meaning, but by contiguity, concepts occurring together in space or time. In the lab, this has been operationalized through stimulus-response tasks, relying on standard word association norms to link words like agony and pain. But this clean, right-angled division does not exist in the human brain. The binary distinction is a methodological artifact. Word associations are actually driven by identifiable semantic relationships. The traditional idea of association assumes that memories can be formed through accidents of contiguity, meaningless spatial or temporal linkages. Yet when two concepts are linked by pure accident, without an underlying meaning, the memory is brittle and quickly decays. By operationalizing semantic and associative memory as separate dimensions, experimental design has been distorted. Researchers have spent years attempting to isolate a pure, association-free semantic memory that simply does not exist. The flaw stems from a severe disconnect between theoretical definitions and laboratory practices. Association is defined theoretically as learning via contiguity, but in a lab, it is measured by a production-based task. A researcher says a word, and the subject provides the first response that comes to mind. These word association norms do not measure accidental collisions in space and time. They measure linguistically based, retrieval-driven responses. To understand how this operational flaw skews the science, we have to reevaluate the classic data across three major experimental paradigms: picture-word interference, the DRM false memory test, and semantic priming. Across all three, treating normative word association data as raw, undifferentiated associative strength masks the complex semantic architecture that actually drives human behavior. If we want to understand word associations, we have to ask why specific words are produced by subjects in the first place. The Santos taxonomy provides a framework for this, breaking down normative word associations into 10 distinct categories based on the relationship between the stimulus and the response. The first three categories, like compound word continuations or sound similarity, are purely linguistic or phonological. They rely on the shape and sound of language, not the mental representation of a concept. Move past the sounds, and the data is dominated by synonyms, antonyms, superordinates, subordinates, and category coordinates. These are direct, definitive semantic relationships. The final category covers an aspect of an object or situation. When a subject hears restaurant and responds with menu, they are actively generating a mental scene. They are relying on a complex semantic script, not a blind associative reflex. Researchers frequently try to test these relations using picture-word interference tasks. They introduce a prime word, wait a fraction of a second, a variable known as the stimulus onset asynchrony, and measure how long it takes the subject to name a target picture. Because up to 90% of this word association taxonomy is explicitly semantic, using these norms to filter out associative effects in those experiments is effectively filtering out semantics itself. In a standard picture-word task, reading a category coordinate, like the word raisin before seeing a picture of an apple, interferes with your ability to name the apple. The cognitive process slows down. Conversely, reading a word associate like pie speeds up the naming process. Historically, researchers claimed this opposing reaction proved a double dissociation, indicating two completely separate mental architectures at play. But cognitive scientist Albert Costa and his colleagues pointed out a flaw in this logic. The associative category is far too heterogeneous to be treated as a single variable. Instead of relying on a semantic versus associative binary, Costa focused on specific types of semantic ties, contrasting strict category coordinates against part-whole relations. A part-whole or situational relationship, like pie to an apple or a stinger to a wasp, causes facilitation. It activates the target's semantic network, but because it belongs to a different conceptual type, it does not compete for the exact lexical node you need to speak. A category coordinate like B belongs to the exact same superordinate group as WASP. Both are valid candidates for selection. This triggers direct lexical competition, which inhibits your ability to name the picture quickly. The observed facilitation is not evidence of a separate associative network. It is simply the result of activating non-competing semantic categories. This misclassification extends into the Dees-Rediger-McDermott, or DRM, false memory paradigm. These experiments test how often subjects falsely recall or recognize a critical word that was purposely omitted from a studied list. Activation and monitoring theory uses a metric called backward associative strength, or BAS, to predict these errors. The theory assumes that the stronger the normative word association from the list items back to the missing critical word, the higher the rate of false recall. To test what this associative metric is actually measuring, researchers Brainerd and Can mapped 55 commonly used DRM lists against strict semantic knowledge types. Their factor analysis revealed that backward associative strength does not operate independently. It loads on the exact same statistical factor as meaningfulness, number of attributes, and situational context. They demonstrated this by building a breakfast list, using words like bacon, eggs, and plate. The list had a mean backward associative strength of nearly 0, yet because it consisted of dense situational relations, it generated exceptionally high rates of false recognition. False memories are not generated by blind associative links. They are generated by the extraction of complex semantic gist during encoding. If all retained associations are semantic, we have to account for laboratory experiments where subjects managed to learn arbitrary, non-related word pairs. A developmental study by Rower and colleagues tested this mechanism directly by administering paired associate learning tasks to students across different age groups. They contrasted the recall of naturally accessible word pairs, like ranch and cowboy, with inaccessible pairs, like ranch and floor. Pre-adolescents struggled heavily to retain the inaccessible pairs, while 12th graders memorized them with significant success. The older adolescents did not rely on raw contiguity or a mechanical memory advantage. They succeeded because they spontaneously deployed elaborative strategies to create meaning out of the disconnected terms. A 12th grader uses their broader knowledge of the world to generate a bridging semantic event, like picturing a janitor refusing to wear velvet or dropping their coffee while playing the harp. This locks the arbitrary pair into a concrete scenario. When the pre-adolescents were explicitly instructed to use these exact same elaborative strategies, their recall performance doubled. Meaningless, arbitrary associations are brittle and decay rapidly. The human memory system requires a semantic framework to anchor long-term retention. This exposes a glaring asymmetry in 30 years of semantic priming literature. Researchers routinely strip normatively associated words out of their semantic testing lists to isolate pure meaning, but they almost never reverse the process to strip semantic ties out of their associative lists. The consequence of this practice is severe. By filtering out word associates, researchers systematically delete the strongest, most viable semantic links from their experimental stimuli. Attempts to find pure associative priming have routinely failed. Even when researchers rely on massive text corpora co-occurrence statistics to measure pure contiguity, they inevitably capture hidden semantic scene relations and category overlaps. Higher than chance co-occurrence in language and the real world is never an accident. It is the semantic system taking advantage of the systematic nature of reality. It is time to stop partitioning experimental stimuli into binary semantic and associative sets. Future research must adopt a multi-dimensional semantic taxonomy, mapping precise behavioral consequences against targeted relation subtypes. Memory is not built on accidents of space and time. Association is the mechanism of learning, but meaning is the architecture of memory.